This is an introduction to Module 9 about the Laplace transform. Basically, we're going to spend some time in 3 sections in the textbook where we are going to study the Laplace transform. We'll begin with the definition, we'll move on to the inverse Laplace transform, and then the Laplace transform of derivatives. And finally, the last section, which will not be covered in this intro, I'll do another short intro to briefly introduce that section 7.3. Just gets us to find Laplace transforms and inverse Laplace transforms of more complicated functions. So we begin section 7.1 with the definition. What is the Laplace transform of a given function f? Well, if I have a function f and I know that it is defined, I can find values for it as long as t is from 0 to infinity, so f of t is defined. Then I can find the Laplace transform by finding this integral from 0 to infinity of e to the minus st times f of t dt. And this is as long as defined to be the Laplace transform as long as this integral converges, as long as we get something and not infinity or minus infinity. You will see in the textbook something about f of t needing to be of exponential order. And what that means basically is that f of t cannot get too large so that this integral can converge. So f of t has to be bounded in some way. So for example, if I wanted to find the Laplace transform of a function t, then I substitute t in place of f of t. And then as you can see here, I have t and then e to the minus st dt. And then I basically, the integral from 0 to infinity means the limit as b goes to infinity of the integral from 0 to b, again, of t e to the minus st. This is an integral that I can do using integration by parts. And if you need to go review that, you should. This will come up a little bit in this section. And using integration by parts and L'Hopital's rule to find the limits, I'm able to arrive at 1 over s squared, which I'll call f of s, a function of s. And the Laplace transform of t being 1 over s squared is something that you also can arrive to from using a table that is given in the first in this 7.1 section. So there will be many times when we can access the Laplace transform of simple functions through the table in this section. There are other times where we cannot do that. For example, if I have a function f of t that is given to me piecewise, meaning that it is one value for a certain range. So this function is t whenever the values of t are between 0 and 1, and then this function is equal to 1 if the values are bigger than or equal to 1. Well, then when I take this integral from 0 to infinity of my function f of t changes values depending on the values of t. So I have to divide it into 2 integrals. Say from 0 to 1, well, in there my function is t, so I can put t for f of t, and then I have that integral. And then if I go from 1 to infinity, then there my function is equal to 1, and I can substitute that instead of f of t. Now I have 2 integrals to solve, and I can do those, the first one again by parts, and the second one is a straight limit integral that I can do. And as you can see, you can pause the video here if you like, and you can get to this, maybe a few steps of this. But you can also see problem number 6 in this section that I've worked out, and it's a sample problem to see another example of this. In section 7.2, we're mostly going to use the table to go back and forth for the inverse Laplace. The idea of an inverse Laplace is that if I take the Laplace transform of a function and it gets me, for example, the Laplace transform of 1 is 1 over s, then the inverse Laplace takes me back. So the inverse Laplace of 1 over s gives me 1, and so on. What's more interesting in this section is that we want to take the Laplace transform of derivatives. And here you can see if I let f prime of t be dv and u is e to the minus st, again I use integration by parts and I arrive at this minus f of 0 plus s L of f of t. Again, I'm going to call the Laplace of f of t f of s, and I arrive at this for the Laplace of that derivative. The same I can do for a second derivative. Now, why do we want to do that? Well, the reason we want to do that is that we can start with an initial value problem and take the Laplace transform. We'll arrive at an equation that has some function f of s. Then we take the inverse Laplace to obtain our solution.